Hello, and thank you for attending the OpenVX talk at Embedded Vision Summit. And today's talk agenda will be highlights and new features of OpenVX 1.3. We'll talk about some common questions about OpenVX. We'll talk about what an OpenVX conformant implementation is, and then we'll move into OpenVX sample implementation, and then we'll talk a little bit about the OpenVX for Raspberry Pi, and then we'll take a deep dive into a case study for an OpenVX cross-platform application. And then we'll conclude with key takeaways and what to look for in the future. And we'll open up the floor for questions. All right, OpenVX is an open royalty-free API standard for cross-platform acceleration of computer vision applications. And OpenVX is from the Kronos group. Those of you who haven't seen Neil's talk, the talk just before me, I would advise to take a look at it after or when you have time. Great information about all the open standards out there. And OpenVX, like we said, it's an API standard. So the first question would be, like, what is an API? So simply put, application programming interface. Without going into the Wikipedia definition, API is a simple messenger which takes your request and goes to a library, application, or a database and brings back a response. So similarly, if you want to put a simple analogy to it, it would be like a waiter. So you would go to a restaurant, you have a menu of items, you choose what you want, you say what your preferences is in that particular meal, your waiter notes it down, goes in, gives it to the kitchen staff, and brings out your meal. So the better the waiter understands you, the better your meal is going to be. So similarly, an API needs to understand its users. So that's the key in any given API. So similarly, an API talking to an application, a library, or a database needs to understand what its user needs and needs to convey that message right, and then bring back the data back to you. So why are APIs important? Right? Like in this day of age, everything is built on each other's work. So if we have a great application, it's not a one person's work. So they're built on top of different libraries, different applications, and different databases. So APIs provide you that building blocks so that you can Lego them together and make something great out of it. And it definitely helps you speed up your development, which is you're not spending time in libraries or functions that you're not very familiar with. So you can quickly use somebody who built a good library and you can use that in your application. So that speeds up your application as a whole. And portability is another issue where API comes to play, is when you have an application that you want to run across different OSs, different hardware, you want to choose an API which supports that. And obviously, the last thing is, if you are not worried about all these underlying issues, you can concentrate more on your application and less on all the groundwork. So that helps better innovation and gives developers more time in concentrating on their key application rather than how and where and what APIs to use. So OpenVX, with response to that, it enables portability, enables performance and power optimized computer vision, especially needed in embedded and real-time systems. And OpenVX is unique in being the only vision API shipped as an optimized driver by vendors. So if you see the block diagram in this slide, you can see there's an application layer and the hardware layer, and OpenVX lies in between that. So it connects your application to the given hardware. And OpenVX underneath can use C++ or OpenCL for its functionality. And that's how it connects your application to the base level hardware. So given OpenVX also was in the framework structure, OpenVX itself has a graph framework. So what it does, it gives the optimizer or the graph optimizer a chance to look into your graph. So when you write an application, it writes it in form of a graph. It can look through your graph pipeline and then choose to fuse a few nodes for better performance. And it can say, okay, I'm going to use a couple of memory blocks, reuse them. So give you lower footprint, and you can deploy this graph across multiple hardware. So this is a key feature in OpenVX. And OpenVX 1.3, so we just released it in October 2019. So the main reason for getting out 1.3 was deployment flexibility and avoiding fragmentation. So as and when an API grows with functionality, so what happens is there are functions which people are interested in, and forcing them to develop all the applications in one big library would make it difficult for them. So just giving them the flexibility of saying, okay, we're going to group a certain number of functions as feature sets, and then allow them to implement that without having to say that you need to implement everything which doesn't concern to you, makes it easier for developers who are developing OpenVX a chance to actually develop the OpenVX. And the hardware vendors can now choose one or more of these feature sets in their implementation and still be fully conformant. And the flexibility of this gives the developer the option of using different vendors' OpenVX across different hardware. So what are these feature sets that are defined, right? So we have multiple feature sets defined. The graph infrastructure is the baseline feature set, which needs to be in every implementation of OpenVX. And then we have the vision, which is the core vision functionality. And then we have the enhanced vision, which is a few enhanced functions which were introduced in OpenVX 1.3. I didn't want to put up all the functions in there. You can always look at the OpenVX registry, because it'll just clog up and now make it simple to read. And then we have the neural network inferencing, and then we have NNEF kernel import, which is another feature where you take your deployment inference model, convert it into an NNEF format, and then import it into an OpenVX graph. And you can run inference across any target hardware. And then we have the binary image, where you can run 1-bit images. And then you have the safety critical reduce feature set for safety certification. So the next thing we wanted to talk about was a few questions about OpenVX. Or a lot of people have these questions or misconceptions about OpenVX, and we wanted to clear them up in today's talk. So the first question is always, is OpenVX an open source library? So it's partly not true, because OpenVX is an open standard API, which is defined by the Kronos work group. And then the vendors actually develop the library and introduce it to the public. So OpenVX is a standard which vendors implement, and then you can get a hold of the library. So you still can do the sudo apt-get OpenVX if there is one, but it's not OpenVX work group that develops it. It's more of the vendors. So the second question is, must I pay royalties and licensing fees to use OpenVX? So a simple answer is no, you don't have to pay any royalties or licensing fees. So it is protected in the Kronos IP framework, and the Kronos members agree not to assert any patent against API used in a conformant implementation. And the third question is, must I be Kronos member to use OpenVX? And that's again a misconception. Members and non-members can actually implement OpenVX, and anybody can use it. So the next one is OpenVX functions limiting? So like I said, we have tight focus on functions which are widely used, rather than choosing to have breadth of all functions. We chose that we're going to have tight focus on most used function, like the vision feature set, the enhanced vision feature set. So there is more tight focus that gives you better optimized functions, and you always can extend the OpenVX with extensions and create custom nodes, and there's full provisions to do that. So we have samples explaining how a user can take an OpenVX implementation and implement his own custom nodes into OpenVX. So, and that comes with a little cost of portability, because if you write custom nodes on one platform, it doesn't really translate to another other platform with another OpenVX. So that's in terms of the portability cost. And the other question is, are implementations different in functionality? So again, not true, because if a person or a company submits a conformance uh, for OpenVX, they have to pass hundreds or thousands of tests which verify and validate each and every function's outputs. So that makes it such that every OpenVX you get does the same way, or it behaves the same. So that's does not hold true for vendor extension and custom nodes, like I said before. And sometimes popular vendor extensions get adopted to Chronos extensions, and then we create a conformance test for that. And that's the progression of how we introduce new functions. And then the other question is, what is a conformant OpenVX implementation? Right? A conformant implementation must pass this exhaustive conformance test suite provided by Chronos to actually use the OpenVX logo. So a vendor takes the APIs and implements his own library, runs it across all these conformance test suite, gets the certification, and then he can say that, or the company can say that it is conformant OpenVX implementation. And these are a few of the vendors who currently have OpenVX implementation. You can see all the major silicon vendors have their own OpenVX implementation. So the next topic I wanted to talk was OpenVX sample implementation. So Chronos group came together, or the OpenVX working group came together and put this sample implementation, and it's open sourced on GitHub. So what this does, it has a implementation of OpenVX available. So it is passing OpenVX 1.3 conformance. And something to note is this implementation is not optimized or production ready. So it is just a sample implementation. So if you want optimized OpenVX libraries, so you are going to go get the vendor implementation, where vendors know their hardware and they implement the OpenVX functionality to get the best optimization on their hardware. So if you want OpenVX for a particular hardware, you might want to go get that vendor's hardware implementation of OpenVX. And so, like I said, the sample implementation is not a reference implementation, which means that a reference implementation supersedes a given spec. So this is not a reference implementation, it's just a sample implementation. So what happens is many people try the sample implementation and say, oh, I did not get that optimization that I was looking for. So I want to say that, hey, if you want to run on a particular hardware vendor, please go get the implementation meant for that hardware. So then you can see that performance boost. So the next one was OpenVX for Raspberry Pi. And we have conducted a couple of OpenVX training in the past in Embedded Vision Summit. And we noticed that a lot of people wanted to have an implementation which runs on Raspberry Pi for them to try out a new function or a new application. So the Chronos group worked together with the Raspberry Pi Foundation, and we just released in July the OpenVX 1.3 conformant implementation for Raspberry Pi. So what this implementation is open sourced on GitHub, and it passes the vision, enhanced vision, and neural net conformance profiles. And this implementation is Neon optimized, and we just submitted conformance for Raspberry Pi Model 3 and Model 4. So again, the community now is taken over this, and now they're working on it and they're optimizing it. And if you want to try out something simple on your Raspberry Pi, feel free to go on the GitHub and get this implementation. So this was the Raspberry Pi website where they had highlighted the availability of OpenVX for all its members or enthusiasts. And that's the quote from Ebden, the chief executive of Raspberry Pi Trading. He was really excited to get this open source implementation for all the people who are using Raspberry Pi. Okay, so now let's talk about the open source OpenVX samples. So we, as a work group, put together a bunch of samples or like applications and put it up on GitHub so that people could just try out simple application, download any conformant implementation of OpenVX, and then just start running an application. Maybe use this as their prototype or use this as a reference for a sample that they want to build. And what we're going to do today is we're going to take one of these open source samples, which is, let me go back here, a skin tone detector sample. And basically it just recognizes your hand and your face. And you could build on top of this application more functionality to it. But so this is just a simple sample which does a bunch of thresholds and ANDs. You can see this graph. It's pretty simple. And if you want to look at the application source code, it's available on GitHub. So what I did is I took this open source implementation of the sample, and I built the Raspberry Pi implementation for OpenVX, built the OpenVX libraries, and then without changing anything on the sample code, I could compile it and run it on the Raspberry Pi. So this is me running the skin tone detector on Raspberry Pi Raspberry Pi 4 Model B using the open source Raspberry Pi implementation. And this is the same application without changing any source code. I just compiled AMD's open source MI X, which actually gives the optimized OpenVX libraries on Windows. And then I was able to compile my application without any change in source code again. And here is me running the sample on Windows 10. So, and I did the same thing, same application, no change in the source code. I built this time with the open source sample implementation from the sample implementation of OpenVX and using an x86 processor on Linux. This is Ubuntu. And again, I could compile and run no problem. So again, no change in any of the application source code. And this is me again using the same source code with AMD's open sourced MI X for OpenVX libraries, and I've compiled it on Mac and just running the same application. So what this shows is me without having to touch anything on my application. I could just build it, no problem, by just using the open source implementation of OpenVX. So that means you could just take any vendor conformant OpenVX and then just compile your application. So it's really portable. And you can see here some tests on performance I did is you can see on the left side here, I have the OpenVX graph unoptimized where I'm not using the graph framework. So what I'm doing is I'm calling one node after the other, like an immediate node. So there's provision for that. It's called VXU nodes. And on the right side, I'm using an OpenVX graph where I'm letting the graph look at the whole application and make those optimizations like merge some nodes or get rid of some nodes which are not really processed. So you can see like some simple application like this, I'm getting like 2.54x on performance boost. And the same thing I did with the memory footprint. So you can see where I don't give the option for the graph optimizer to look and make those memory optimizations on the left where it's just using every buffer that I said it to use in the application versus the optimized where the graph looks at the whole graph and says, okay, I'm going to reuse these buffers because I don't need to keep the intermediate data. So it almost reduces to 0.2x. So that's like a great saving. So especially if you're using an embedded system device where the memory is already in short supply, these kind of optimizations really push your boundaries to make a better application. So again, for these two samples, I use the optimized OpenVX libraries from open source MIVisionX from AMD. And conclusions. So the key takeaway today is, as a developer, or at least for me as a software engineer, when I'm looking to develop an application, the first thing I want to do is make sure that the APIs that I'm going to use in my application are are well thought about and are portable and are optimized. So if you use an API which is not portable, you might have to make those updates into your application every time you want to move it across one hardware or an OS. So if you don't want that, you might want to think before you implement your application to take care of these kind of things. And like I said, OpenVX is unique in being the only Vision API shipped as optimized driver, and OpenVX delivers comparable performance to hand-optimized non-portable code. Why I say that is, if you are using an x86 processor from some vendor and you download their optimized OpenVX, they know their hardware best. So they have written the OpenVX for their hardware, and it gives you the best performance. So for you as a developer, you don't have to worry about, oh, is my underlying functions optimized? So it's already given to you. So you can spend more time improving, making your application better than rather worrying about the underlying functionality. And acceleration on wide range of vision hardware. Like I said, a lot of the silicon vendors have an implementation of OpenVX. So make sure to, like, if you are trying to use their hardware, to download their optimized OpenVX into your application so that you get the best performance. And then, like I said, the graph-based abstraction always helps you get the best in performance and best in memory footprint. So those kind of things are given for you for free. And like I said, portable, efficient vision processing. And hope you guys try out the OpenVX from our OpenVX samples when you get a chance. And a few acknowledgement. Any talk doesn't really represent one person's work. It's always a lot of people helping each other. So I would like to thank Mike, AMD's MIVisionX team, the OpenVX work group, Neil, and the Embedded Vision Summit 2020 organizers for all their inputs and helping me put together this good talk. And here's a resource slide. I put all the information that I've given in this slide. So if you want to download any of the open source implementation or get the samples or get some tutorial material, all is available in this recite slide. And I think this will be available for you at the end of the talk, so you can download the slides and get these resources. And some disclaimers and attribution. And all right, thank you.